Welcome to a deep dive into a fascinating corner of the cosmos, one that's often overlooked. White dwarfs.
Yeah.
You see, while they might be called dwarfs and they might be remnants of stars, don't let those terms fool you. This isn't some quiet graveyard of space.
No, not at all.
We've got a stack of scientific papers right here, and let me tell you, these stellar remnants are bursting with activity, full of surprises, and honestly, they hold some pretty big clues to the fate of our universe,
hmm
including our own sun.
It's true. White dwarfs are everywhere. They're not just some cosmic oddity. They represent the final stage for the vast majority of stars in the Milky Way,
Yeah.
our own sun included.
I've got to admit, the idea of our sun becoming a white dwarf billions of years from now is both awe-inspiring and a little bit eerie.
Right.
What does that look like, that transformation?
Well, picture this. The sun, having exhausted its nuclear fuel, will swell into a red giant,
Oops.
engulfing the inner planets. Then it shrugs off its outer layers, leaving behind a core that's been compressed to about the size of Earth. That's your white dwarf. A cosmic heavyweight crammed into a surprisingly small package.
So we're talking incredibly dense objects, right? And we actually know about 250,000 of these white dwarfs already.
We do. And here's the thing about density. There's a limit to how much mass a white dwarf can handle before things get, well, explosive.
Uh-oh.
It's called the Chandrasekhar limit, and it's about 1.4 times the mass of our sun.
Okay.
Anything heavier than that, and the white dwarf can't resist the pull of its own gravity.
A cosmic game of chicken with gravity. Those white dwarfs definitely keep things interesting. But what's going on inside these stellar remnants? What can you tell me about their structure?
Imagine peeling back the layers of a cosmic onion.
Okay.
At the heart of a white dwarf lies its core, and this is where things get really mind-blowing.
Right.
Most white dwarfs have cores composed primarily of carbon and oxygen.
Carbon and oxygen, isn't that what stars burn as fuel?
Exactly. These are the leftovers from a star's long life of nuclear fusion. The very processes that make stars shine. But here's the kicker. As a white dwarf cools over billions of years, that carbon and oxygen core doesn't just sit there.
Yeah.
It undergoes a process called crystallization.
Crystallization. So the core of a star turns into something like a giant diamond in space.
You're not far off. It's similar to water freezing into ice.
Okay.
But instead of happening at a chilly 0 degrees Celsius, this crystallization occurs at millions of degrees.
Oh, wow.
Imagine the pressure inside that white dwarf, forcing the carbon and oxygen atoms to lock into a rigid crystal lattice structure.
That's incredible. So these white dwarfs have diamond hearts.
Yeah.
But what's the significance of that? Why is this crystallization such a big deal?
It's not just about bling. This crystallization process actually releases a tremendous amount of energy.
Wow.
It's like the white dwarf has a hidden reserve of energy that allows it to keep shining and radiating heat for even longer than we initially thought.
A hidden energy source inside a crystallized core. These white dwarfs are full of surprises. But the papers we've got here mention more than just a dazzling core. There's talk about pulsations, too, almost as if these white dwarfs have a heartbeat.
And what a fascinating heartbeat it is. You see, a small percentage of white dwarfs, about 2–3%,
Okay.
display these periodic variations in brightness.
Right.
They're not random fluctuations, they're more like starquakes, offering us a glimpse into the hidden layers of these stellar remnants.
Starquakes, that sounds intense. What can we learn from these cosmic tremors?
These pulsations, much like earthquakes on Earth, send ripples through the white dwarf.
Okay.
By studying these ripples, astronomers can actually decipher the internal structure of a white dwarf, its composition, its temperature, even its age. It's like listening to the faint echo of a star's life long after its primary fuel has been spent.
It's incredible to think that these subtle variations in brightness can reveal so much about these ancient objects.
And it's not just the core and these pulsations that are fascinating.
Right.
Some white dwarfs possess another remarkable feature: magnetic fields millions of times stronger than Earth's.
Wait, hold on. Magnetic fields. We're talking about remnants of stars here.
Right.
Where are these powerful magnetic fields coming from?
That's a question that has puzzled astronomers for quite some time, and it speaks to the complex processes happening both during and after a star's death.
Okay.
But what we do know is that these magnetic fields can have a profound impact on the white dwarf's evolution. And as we delve deeper into these white dwarfs, we encounter even more intriguing questions.
Okay.
One that always sparks curiosity is the possibility of planets orbiting these stellar remnants.
It's a wild thought, right? We're talking about the aftermath of a star's demise,
Yeah.
potentially a chaotic environment.
Yeah.
How could planets even survive, let alone exist in such a setting?
You're right, it's a puzzle.
Yeah.
With a few compelling pieces.
Okay.
We know that when a star balloons into a red giant, any inner planets are likely engulfed.
Right.
But those further out, their fate is a bit more uncertain. One possibility is that these outer planets migrate inwards after the star becomes a white dwarf, drawn in by its still considerable gravity.
So like a cosmic reshuffling, planets rearranging themselves after the main event.
Precisely. But it gets even wilder.
Okay.
Another possibility is that entirely new planets could form from the debris left behind by the star's transformation. A cosmic phoenix rising from the ashes, you could say.
Now that's some serious cosmic recycling. But let's say you've got a planet lucky enough to be orbiting a white dwarf.
Right.
What's life like in such a system?
Lucky might be a strong word. Imagine a world tidally locked to its star.
Okay.
One side perpetually bathed in daylight, the other in perpetual darkness.
Right.
This isn't just about extreme temperatures, though that's certainly a factor.
Yeah.
Tidal locking can wreak havoc on a planet's atmosphere, potentially causing it to collapse on the dark side.
Okay, so we're talking about a world of extremes, scorching heat on one side, unimaginable cold on the other, and an atmosphere struggling to hold itself together. Not exactly a walk in the park, but these papers mention the discovery of an actual planet orbiting a white dwarf, a Jovian-like planet, no less.
Yes, and this discovery was a game changer. It upended our assumptions and opened up a whole new realm of possibilities.
Wow.
Here we have a gas giant similar in size to Jupiter,
Right.
orbiting a white dwarf.
Yeah.
It begs the question, how common are these systems, and what can they teach us about planetary evolution in the most extreme of circumstances?
It makes you wonder if there are other planets out there, perhaps smaller, rocky worlds, also clinging to existence around these white dwarfs. And if so, could any of them, against all odds, harbor life?
That's the million-dollar question, isn't it? While the conditions around white dwarfs might seem inhospitable at first glance, life is incredibly adaptable.
Right.
And remember, we found life thriving in some of the most extreme environments here on Earth.
Yeah.
From deep-sea volcanic vents to the frigid, dry valleys of Antarctica.
So even in this cosmic graveyard, there could be sparks of life clinging to existence. It's humbling and awe-inspiring at the same time.
It is.
But let's shift gears a bit. We've talked about what's inside a white dwarf, and we've touched on the possibility of planets orbiting them.
Right.
What about their ultimate fate? What happens to these stellar remnants over time? It's almost poetic when you think about it. These white dwarfs, remnants of once mighty stars, still evolving, still holding secrets to the universe's grand story. But what's their next chapter? What's the ultimate fate of a white dwarf?
Well, in a sense, their fate is written in their name.
Okay.
They cool down slowly, fading from white to black.
Right.
We're talking about timescales that are almost unfathomable, trillions upon trillions of years.
Wow.
Until they become what we call black dwarfs.
Black dwarfs, the universe's cooled embers.
Yeah.
It's both beautiful and a little melancholy.
Yeah.
But I've got to ask, with all the mind-bending things we've learned about white dwarfs already,
Right.
is there a chance they go out with a bang?
Okay.
Could they explode?
It's a question that has captivated astronomers, and the answer, surprisingly, might be yes.
Really?
While it was long thought that black dwarfs would simply fade into oblivion,
Right.
recent research suggests a more dramatic possibility.
Okay.
Black dwarf supernovae.
Supernovae.
Yeah.
From objects that are essentially dead stars, how is that even possible?
It all comes down to a slow, subtle process called pignonuclear fusion.
Okay.
Still happening deep within the cores of these black dwarfs.
Wow.
Even though they've exhausted their primary fuel, they're so incredibly dense that lighter elements are still being forced together, creating heavier ones.
Okay.
And over those unimaginable timescales, the end product is iron-56.
Iron. Isn't that significant? Didn't we talk about iron earlier in relation to white dwarfs?
You've got a great memory. Remember the Chandrasekhar limit?
Right.
That critical mass a white dwarf can hold before collapsing?
Right, yeah.
Well, as iron builds up in the core of a black dwarf, it actually changes the electron fraction within the star.
Okay.
And here's the crucial part, the Chandrasekhar limit. It's dependent on that electron fraction.
So as the electron fraction changes because of the iron buildup, that limit gets lower.
Exactly. The more iron accumulates, the lower the Chandrasekhar limit becomes.
Wow.
And eventually, if the black dwarf is massive enough to begin with,
Yeah.
that limit dips below its actual mass and Well, you can imagine what happens next.
Boom! A delayed supernova triggered by processes happening over trillions of years.
Yeah.
That's absolutely mind-blowing.
It's a powerful reminder that even in the face of what seems like cosmic death, the universe finds a way to surprise us.
It really does.
But here's the catch. These black dwarf supernovae are predicted to occur so far in the future that it's almost impossible to grasp.
Oh, okay.
We're talking about 100 years from now.
Yeah.
To put that in perspective, if the entire lifespan of the universe to this point was just 1 second,
Okay.
we're talking about events happening trillions upon trillions of years after that single second.
I don't even have words. It's hard to even imagine. But it does make you think, what will the universe look like at that point? And will anything remain of these explosions, these last gasps of energy?
Those are questions that will keep cosmologists busy for millennia to come.
I bet.
But one thing's for sure, by studying white dwarfs, these seemingly quiet remnants,
Yeah.
we're not just looking into the past,
Okay.
we're catching glimpses of the universe's distant future, perhaps even its final act.
It's both humbling and awe-inspiring to consider those timescales and processes.
It is.
But before we wrap up, I'm curious, are there any other surprises lurking around white dwarfs? We've talked about their cores, their potential to explode, even the possibility of planets around them.
Right.
Is there anything else these stellar remnants can tell us?
Remember those debris disks we mentioned?
Yes.
The ones that could form new planets?
Oh, right. We kind of glossed over that earlier.
Yeah.
What kind of clues are we talking about? How can we learn about long-gone planets just by studying dust and debris?
It's all about reading the cosmic fingerprints left behind.
Okay.
By analyzing the composition of these debris disks,
Right.
astronomers can glean insights into the types of planets that once orbited the star.
Wow.
For example, finding high concentrations of heavier elements like iron and magnesium could point to the existence of rocky Earth-like planets in the system's past.
So even though those planets are long gone, their chemical signatures remain swirling around their dead star.
Right.
It's like a bittersweet cosmic echo.
Exactly. And the more we study these debris disks, the more we realize just how dynamic and complex planetary systems can be.
Yeah.
It's a reminder that our own solar system, with its familiar planets and orbits, is just one snapshot in a much grander, more chaotic cosmic dance.
It's mind-boggling to think about those scales, planets forming, evolving, and ultimately meeting their demise as their star transforms into a white dwarf, leaving behind just a whisper of their existence in a cloud of dust.
It is pretty amazing.
And with that thought, I think we've reached the end of our deep dive into the fascinating world of white dwarfs. From their diamond hearts to their explosive potential, these stellar remnants have certainly given us a lot to ponder.
Now,
A big thank you to our expert for illuminating this corner of the cosmos for us.
my pleasure.
And to all our listeners out there, keep looking up and never stop questioning the universe around you.